for lecture 3 here by John. One thing I wanted to mention is Anna has created kind of detailed lecture notes with some extra examples and filled in some proof details and legibly written very nice in multiple colors. And those are on the web page now as well.
Wow, I'll look
Yeah.
at them.
Yeah, I found reading those is almost like a new format that's even better than a paper. So I call it the Poon format that's coming up. Anyway.
I'll learn something, I'm sure.
Yeah, right. Okay, anyway, take her away, John.
Thanks very much again to Anna and Jim. Let me continue. So last time we discussed the conjecture that these chromatic quasisymmetric functions are E positive when the graph in question is an incomparability graph of a natural unit interval order. So what I want to do this time is present evidence that also opens up a good way of thinking about these things. So let me write the theorem. So the theorem, I'll write an abbreviated version. So we start with one of these Hessenberg vectors, and then what I want to claim here is that if I take the chromatic symmetric function of the incomparability graph of the associated unit interval order, but it would probably be good if I use my own. We could learn some low dimensional topology, I suppose, but I'm not qualified to explain much of it. So we have this chromatic symmetric function here of this unit interval order or unit interval graph, and the claim is it's sure positive. Okay, I'm going to give a much more detailed theorem with a formula, right? So this is good. First of all, any E positive symmetric function is sure positive. So this is evidence, right? The other point is a sure positive symmetric function, right, is nothing but the Frobenius characteristic of an actual representation of the symmetric group. And so the idea now is associated with this Hessenberg graph, we have a representation, we can attempt to analyze it in other ways. And what is this representation? So we're going to have a formula for decomposition of this representation into irreducibles once we state an exact formula for the multiplicities, right? And the first comment I want to make is that the big ideas here were already found and proved by Gesharov in the case that T is 1, right? For 3 plus 1 free, right? So our GMs are incomparability graphs of 3 plus 1 and 2 plus 2 free posets. So this is a much larger class, but he was doing the ungraded case. So the idea here is for one of these graphs, you get a representation. Our representation is graded. It refines the representation you get when T is 1 and you have an actual chromatic symmetric function, right? And what I want to say is that our proof very much follows Gesharov's, but not exactly. So there's going to be some kind of involution that preserves certain statistics. And we have an extra statistic, basically the power of T that's involved. So we approach it exactly the same way that Gesharov did. The real ideas are his, but we cannot use his exact involution. We have to find our own involution that makes his proof go. But the key ideas here you can find in his work, and his work applies in an ungraded case, but to a larger class of incomparability graphs. Okay. So here's a more specific theorem. We're going to have an actual formula. And this, again, just refines Gesharov's formula. So let's say we're given any poset P with vertex at 1 through n and a partition of n. And then I want to define a p-tableau of shape lambda, right? is a filling of the Young diagram. Of shape lambda with 1, 2 up to n, used once each, right? So that, well, two things are satisfied. The rows are p increasing. That is, as I move to the right, I go up in the poset P, strictly up, and columns have no P decrease. When I move down a column, I never decrease in the poset, right? So let's just look at some example. So let's take our Hessenberg vector is, I don't know, 2, 3, 4, 5, 6, 6. So then we have this poset. How does it look? This says that 1 sits below 3, 4, 5, and 6, 2 sits below 4, 5, and 6, and so on. Looks like that. All right, that's our poset. All right, and our graph looks like this. All right, so let's take lambdas 3, 2, 1 and ask what a p-tableau of shape lambda looks like. So here's one. 2, 4, 6, 1, 3, 5. Right? That's a p-tableau. Right? So first of all, as I move from left to right in a row, I see a chain. I move up along a chain in the poset. So 2, 4, 6 is fine. 1, 3 is fine. This 5 is fine by itself. As I move down a column, I can decrease in the usual order on these integers, but I cannot decrease in the poset. This is fine because 2 and 1 are unrelated, right? So in general, when I move down a column, I'm either going to see a numerical increase or a numerical decrease between elements that are unrelated in the poset. So this is perfectly good. Right? This is a good example, right? And now associated to this, we need a statistic, right? An inversion. In a p-tableau, let's call it T, right, is a pair I less than J, with I and J incomparable. So they live in the edge set of our unit interval graph, right? And I is in a lower row than J in T. Okay, so this is some kind of inversion, right? And so in this tableau, right, we have this inversion here, this inversion here, and this inversion here. Right, the edges just go from I to I plus 1, so we're looking, right, for pairs I plus 1 such that I lives below I plus 1. Right, so 2, 3 is not an inversion because 2 is above 3. Okay, so here, right, these relate to the graph, right? This has 3 inversions. Okay, so far so good. All right, so the theorem. Well, I guess I need some more notation. There's too much notation, but there's not much to do about it.
John, can I ask you a quick question?
Sure, go ahead.
Why is it just I and I plus 1? Because you wrote I less than J, so wouldn't 1, 4 also be an inversion?
No, because 1, 4 is not an edge in this graph.
I see. Okay, thank you.
Does that make sense?
Mhm.
Great. Okay, so I just need some more notation. I don't like so much notation, but I guess we need it, right? Is number of p-tableau, or the set of all p-tableau. Shape lambda. Right, and here's the real theorem. This is the sum over all partitions of n. Well, then we have S lambda, and I'm going to tell you the coefficient of S lambda, and this is the sum. It's maybe what you expect. We take all the p-tableau of shape lambda, right, and we raise t to the power number of inversions. Okay, so the key point here is this has positive coefficients, manifestly. Right, so this says that we're sure positive, right? The coefficient of every sure function is a polynomial with non-negative integer coefficients. If we want to think of this sort of as a graded representation, of course, we collect all the S lambdas connected to t to a particular power. Right. Okay, so let's have a look. All right, I would like to do an example before we go through a proof. Right, the proof is going to take a while and be complicated. I found it's some combination of fun and pain to give these talks because the organizers demand, rather than just filibustering about what are the attractive ideas, you actually convince everybody that you have proofs. And so this takes some work, but it's kind of fun. It's a fun change. So, but I would like to show you an example. Let's take M is 233, sorry. So then this graph looks like this, and the poset looks like this. 1 lives below 3, 2 is not related to anything. Right? And so now, right, we need all the p-tableau. So the first thing, there's no p-tableau here. Right, because what it would mean is I'd have a chain of length 3 in the first row, and there is no chain of length 3. Right, lambda is 2, 1. Well, now my only choice is to put the chain 1, 3 in the first row, right, and 2 in the second row. And now there's an inversion here, right, and so there's one inversion, and finally lambda is 1, 1, 1, right? And now we have this, right? The condition that there's no decrease in a column means that I cannot have 3 directly above 1. That's exactly what it means. 3 is related to 1 in this way, so I'm missing the 2 permutations in which 3 lives directly above 1. This has no inversions. This has 1 inversion. This has 1 inversion. This has 2 inversions. And the claim now of the theorem, which we've seen verified several times, is that this is S3 plus T times 2S3 plus S21 plus T squared times S3. Sorry, 1, 1, 1, 1, 1, 1, 1, 1, 1. All right, well, I'm used to applying the involution for reasons that we'll see later. All right, so there are this one and this one, they come here. This one here comes here, right? This one here comes here, and this one here comes here. Right, and this matches what we've done in several guises before. Okay, so that's the theorem, right? And so it gives a concrete formula which allows you to compute the multiplicities the graded multiplicities of the Schur functions in this chromatic symmetric function, or graded chromatic symmetric function. Right.
Oh, John, Maria asked an interesting question in the chat. Is there a Madge version?
What do I wish? Is Michelle here?
No, I don't think she's here.
Let me say, in this particular case, right, in this particular case with the string graph like this, there is. And you can see that in a different paper. In the general case, off the top of my head, I am not sure what to say, and either Michelle or I will address this later. So the answer is, unfortunately, I don't know. Sorry.
That's really cool. Thanks.
There's a connection between these and LT polynomials, and there's no Madge version of LTs, so maybe that's kind of related.
Not yet.
Yeah, that is correct. In the string case, you can say many different things. That's a different subject.
John, a slight follow-up on Maria. You said that it doesn't work in general with Madge, but when it does the polynomial agree with the inv?
This is, say again, so when it works with the Madge, what I can say is in the string setup, this thing is very closely related. In fact, allows us to compute the joint distribution of a major index and exceedances. Right, and in fact, that's how a big part of how we discovered the theorems I'm showing you. Right, but it requires some change, right? So somehow using principal specialization, this T will encode an Eulerian statistic, and then with the correct specializations, right, this symmetric function, this part here will encode some kind of Mahonian statistics. That's the idea, but it only works nicely as far as we know with these strings. Sorry, Teddy, I don't know if that answered your specific question. Was it?
No, I think it is. It's good for now.
Okay. So, all right. Yeah, I'm happy to discuss more. Thank you all. I'm sorry those answers were not as responsive as I would have liked. Okay. So, yeah, I want to describe the proof. And I'm going to give much of the proof. To give it all, we'd be here forever. Right. So, for proof, here's, we need to use something I'm not proving. And so I'll just say this and ignore it for a while. So we had the right, the definition, and I used essence, but you can use descents also. All right, and this is maybe not totally obvious, right? But it's true. You get the same answer if you count descents, which are edges labeled sort of opposite. You know, the labels have the opposite relation as the vertices, right? And I'm going to need this, actually, at least the way we've written the proof down. And I just ask that you take this on faith, and maybe in one of the later lectures, there'll be a discussion of this. So you certainly have defined. Go ahead.
John, I think there is a simple reason for this, that because it's a symmetric function, you can replace I by n minus I plus 1 for all.
You have to know what n is, right? I guess you're correct, right? I guess you take the largest color used. This is a good point.
Yeah.
This is, you take the largest color used and you just reverse the colors. The smallest becomes the largest and so on. And then you have a good count. Thank you, Jim. That's absolutely correct. That's absolutely correct. You just reverse the colors used. That's right. Okay. we make some other claim in the paper. We go to quasi-symmetric functions and, you know, bases and so on, but I think you're absolutely correct. Okay. So we're going to need this, and now I need a bunch more definitions. So these are all, right, these definitions were made by Gasharov, all the definitions he had. So we want to define something more general in a p-tableau. So we're going to take a weak composition. So just a list of non-negative integers and non-negative integers adding to n, right? And now I'm just going to define an array. It's like a tableau, except it has weaker conditions. And I'm going to give a slightly informal, at least I'm going to say it differently than we do in the paper. So I'm going to take a set partition. And it's going to satisfy two conditions. Well, the first is it's kind of got the same type. Right. And each pi I is a chain. Right. So we'll call this PM. Well, I'm calling it an array, but it's like a tableau. So there, it's weakened in two ways, right? The first thing is the shape we're filling is not a Young diagram of a partition. It's a supposed Young diagram of a weak composition. So there are some empty rows. The rows don't get shorter as you go down and so on and so forth. This condition we had before, right? We're in fact going to write this chain in increasing order, just like we did in the tableau, right? But we have no condition on the columns. This is a key point. There's no condition on the columns at all. It's just increasing P, increasing across rows, right? So let's just take a quick look. Right, so here's a P array. That's an empty row. Right, like this. Right, and we can define inversions the same way. Right, so we have this pair, and this pair, right? Those are the inversions, right? So this is more general, right? And a key point I want to make is this wouldn't be allowed in a tableau, right? This is something illegal in a tableau, but it's completely legal in one of these arrays, right? So we're going to use these. The idea is, so every, right, P tableau is a P array, right? But not vice versa. There are way more of these. Okay. So this is the key definition, and now we can start the proof. Right. Although I'm going to throw in some examples. So we're going to just isolate a particular lambda. All right, so this is what we want. Compute. The idea is that we are first going to write a formula for this coefficient, not in terms of tableau, but in terms of arrays. Right? We're going to write in terms of certain arrays. They will not all have shape lambda. Right? That's what we're going to do first, right? And then the accuracy of this formula will be proved using symmetric function manipulations. And then using a nice involution, a statistics preserving and or reversing involution, we will show that the formula using arrays matches the formula in the theorem, which uses tableau. That's the plan. Okay. So there are more definitions needed, right? And so, I mean, this will be something familiar once we unravel it. So we take some W and Sn, right? And we're given some lambda. We want to make a weak composition. Well, sometimes it'll fail to be a weak composition. This is lambda sub W of I minus W of I plus I. And here I runs from 1 to n. Okay. So I'd like to show an example here. Right. So right. Actually, this is a bad one. Lambda is 210. So the first thing I want to do is extend. I have a partition of n, right? I'm going to extend it until it has n parts, right? So if W, right, and W of lambda, so if W is 1, 2, 3, nothing happens. If W is 1, 3, 2, right, then what do we get? Well, we get this 2, just like before. Right, and now the second entry, right, is lambda 3, which is 0, minus 3, plus 2, which is minus 1, and this here is 2, because they're always going to add the 3, and this we don't like at all. Right, that we just are never going to count. That's not a composition. 2, 1, 3, right, what's going to happen there? Well, we're going to get lambda 2 minus 2 plus 1, right? Then we're going to get 3, 0, and so on, like this. Okay. So this doesn't count. This counts, right? This is a good composition, right? And so now the claim, right, is that C lambda of T is the sum, well, sorry. I need another definition. A of P lambda, right? This is a set of pairs, AW, right, such that W is a permutation, and A is a p-tableau, sorry, PM array of shape W lambda. Okay. All right, so this is starting to get very heavy in notation and messy, and I would like to show you another example. Right, instead of 2, 1, 0, I want to start with 1, 1, 1. All right, so here n is 3, and again we're going to take m as usual is 2, 3, 3. Right, so this PM like this. All right, so let me run through this. right? I don't want to do every single detail. All right, so here we get 1, 1, 1, nothing changes. Here we have 1, 0, 2. All right, here we have 0, 2, 1. All right, these are not too hard to compute. 0, 0, 3, minus 1, 2, 2, all right, and minus 1, 0, 3. So these don't count. We just ignore these. And now I would like to list for each of them, right, all the p arrays of this shape, right? And so here we have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1, because there are no restrictions on the columns, right? For this one here, we need one thing in the first row, that has to be a 2, nothing in the second row in the chain 1, 3 here, right? Here, right, we need nothing in the first row, the chain 1, 3 here, and 2 here, and here there's nothing, right? There's no chains of length 3. I would need 2 blank rows and a chain of length 3 in the third row, right? So associated to this permutation, we have 6 arrays. Associated to this permutation, 1. Associated to this permutation, 1. And associated to these 3 permutations here, nothing, right? And the claim is that the coefficient of S lambda, right, which we want to express in terms of tableau, we can at least express in terms of arrays. Okay. Let's take a look at this example. All right. So let me write the number of inversions here: 0, 1, 1, 1, 1, 2. So Eulerian statistic. The number of inversions here is 1. The number of inversions here is 1, right? So 2, 1 is an inversion here. 3, 2 is an inversion here. Okay, so now, right, according to the claim, right, example, C11 of t, right, is, well, 1 plus 4t plus t squared. That comes from 1, 2, 3. Right, minus, these two are odd permutations, they're transpositions, 2t, right, 1, 3, 2, and 2, 1, 3. 1 plus 2t plus t squared, which is exactly what it was somewhere up here. Right, here's S11, there's 1, 2 t's, and t squared. So this is the claim. So there are 2 things to prove: the proof that the claim is true and the proof that the claim implies, right, the actual claim of the theorem. Right? So I think I'd like to do the second first. Now's a good time again to pause to see if anybody has any comments or questions. Okay. I'd like to do the second first. Let me remark that proving the claim is basically the Jacobi-Trudy identity, along with understanding orthonormal bases or dual bases for the space of symmetric functions. It's going to be mostly a symmetric function manipulation, right? There's one more comment. Each array corresponds to a proper coloring with colors 1, 2 up to n, right, the elements in row I get color I. Right? The fact that the elements in a given row have to be a chain in P exactly mean that they have to be an independent set in the graph G. Right? So here I give color 1 here and color 3 to these two vertices. That's a perfectly good coloring. And so on, they write color 2. One thing you might notice in this setup is we didn't use all the possible colorings. And that's true, but it doesn't matter. Right? There are some good colorings that we didn't use. So what's going to happen? Well, what we really know, right? The goal is to prove that this thing here is a sum of these things here, but just over the tableau. So among these arrays here, right? This one is a tableau. This one is a tableau. This one is a tableau. And this one is a tableau. Right? So the goal, in fact, is to get some bijection that cancels these two with these two. And you see they have the same number, right, of inversions, 1, 1, 1, 1, right? But they have different signs. They are associated to permutations with different signs. So the idea is to get a involution on this set, right, which only fixes the tableau, these things here, right, and then is inversion preserving and sign reversing on the remaining arrays, right? That's basically the story. So we have to pair these off, and in this picture, maybe you believe there's a fairly obvious way to pair them off. We pair these two and these two, right, by taking this 3 and moving it into the hole. Right? So the proof is some generalization of this picture. Right? And I certainly don't have time to tell you, to convince you it works, but I want to tell you what it is. Right? So how does the claim imply the theorem? Well, it implies it just like I said, right? So here's a first observation. If I take one of these legal tableaus, then with the identity, it becomes a legal array. Right? And if W is not 1, then W of lambda is not a partition. Right? So, I mean, there are some examples, right? None of these is a partition. That's straightforward to confirm if you're keeping track of the notation. Right? Right? And therefore, if I take some W array, right, then this A here is not a legal tableau. So the legal tableaus all live here with the identity permutation. Some non-legal arrays, some arrays that are not tableau live here also, but living with a non-identity permutation, you never see a tableau. And the idea is now, like I said, to define a bijection, right, on the remaining. So we're going to define, just need some notation, B P lambda. Right? This is the things that are not tableau, essentially. Right? Okay, and so find EG preserving sign reversing involution on this set of non-tableau, right? This, if we can do this, we're done. Because then, right, the formula, right, involves the signs and the inversions, right? The tableau, the ones where A is a tableau and W is 1, they're going to be left alone. They're going to give exactly what the formula in the theorem claims, right? Because the sign is going to be 1, and we're just going to get t to the sum inversions over all the tableau, and everything else is going to cancel because the signs are going to be reversed and the inversions are going to be preserved. Right, so this is what's necessary, and let me just tell you what it is if I can manage. Right, so let's say we have something we want to pair off. Let's call an entry of A bad, for lack of a better word, if either let me call this alpha. There is no entry of A directly above alpha, or right, the entry beta directly above alpha satisfies beta is bigger than alpha in our poset P. Okay. So this is sort of, we put, when we had these arrays, we put no column conditions. So they differed from the tableau. And now we're saying, well, they differ from the tableau because they violate the column condition. That's bad. Or, well, we have something that's not a partition, right? So there's some row that's longer than the row above it. That's also bad, right? It's not a tableau. So these are things that make this A not a tableau, right? And if either of them happens, there's a bad entry. So every one of these pairs, there is a bad entry because this A is not a tableau, right? Not a legal tableau. So there's always a bad alpha, right? Find the leftmost column C in A containing a bad entry. Right. In column C, find the lowest bad entry. Let R be the row above the bad entry. Okay, so I guess let me just pick one of these examples here. All right, here's 2 blank 1 3. All right, well, this is bad and this is bad, right? Because they both have nothing above them. This is leftmost, right? So this is the leftmost lowest bad entry, right? And so what we see is that R is 2 because the bad entry is in the third row and C is 1. Okay, so we're picking a particular bad entry, sort of the westmost, and then given westmost, also the southmost. Okay. And now there's a bunch of definitions. We're going to use this bad entry to get our involution. Okay. Let CR of A be the set of entries in row R weakly to the right of column C, and CR plus 1, here we have a strict condition, be the set of entries in row R plus 1 strictly to the right column C. Okay, so here's a picture. Here's the bad entry, R plus 1. Here's column C. There might be stuff here, there's stuff here, right? And there's stuff here. And I'm going to pick all of this, right? Here's the bad entry. And I'm going to pick all of this. Okay. That's how it looks. Right? And now I'm going to define a subgraph. H of A is the subgraph of GM induced on CR of A union CR plus 1 of A. Right? So there's some subgraph induced here. This subgraph is bipartite. Right, because this is an independent set and this is an independent set. This is a bipartite graph, right? And now I need more definitions. For I in R or R plus 1, right, we're going to define OI. O stands for odd. These are all alphas in Ci of A, such that alpha is in a component, connected component of odd size in this graph H, right? And EI of A is, well, Ci of A minus OI of A, things in components of even size. The key point about these definitions is that if I have something in this row in an odd component and something in this row in an even component, there's no edge between them because they don't live in the same component. This is key point, right? And this is just some way of splitting things. And then I need another thing, which I'll call big I sub little I of A. Right, this is entries in row I, but not in Ci of A. So the I is everything that lives over here. Okay. And now what? Right. We can exchange OR of A with OR plus 1 of A and replace W with W times the transposition OR plus 1. This is how it works. Okay? This is a inversion preserving sign reversing involution. Okay, it's certainly sign reversing. There it is. We multiplied by a transposition. The key point is that this remains an array that lives in the same family, right? And so I guess I want to give you some idea why we can actually do this. Why we can actually do this. Right? And I want to make another comment. What you'll see is why we can actually do this is really depends only on 3 plus 1 free. This is not the same involution as Gesharov uses, but like his involution, it only depends on 3 plus 1 free. The 2 plus 2 free is just used to guarantee that in the graded case, we have a symmetric function. Right? So this is only going to depend on 3 plus 1 free. right? So what's going to happen, right? So to prove this, we need that CR of A union ER of A union OR plus 1 of A is a chain. PM. This is what we need. So we know that everything in here is below everything in here, right? These things here, let me scroll up. I'm in row R, right? The things, sorry, this is IR. The things in here, this is a chain, and IR are the things that start the chain, and ER are some of these, right? The things in OR plus 1 are not related to the things in, or sorry, are related to the things in ER. That's what I was talking about before, right? That this is the reason we're breaking into even and odd, right? There cannot be an edge between something here and something here because they live in different connected components. So there are no edges between the things in ER and OR plus 1. Therefore, the union of this and this is a chain, right? It means that everything in here is related to everything in here. These are chains, and therefore the union of this is a chain. So the key point is to show that everything in IR lives below, right? To show if, what do I want to say? Alpha is in IR of A and beta is in OR plus 1 of A, then alpha is less than beta in this poset. That's the key point, right? Of course, you have to do something similar for IR plus 1, ER plus 1, and OR, right? But the idea is just the same. Okay, so how does this look? So we're in row R. Here's row R plus 1. Up here is column C, right? Here's the leftmost lowest bad thing, right? Here's alpha, right? And here's beta. So what am I going to look at? Well, I'm going to look at, let's say, mu, some delta here. Let me call this epsilon, and some delta here. All right. Well, what do we know? This thing here is bad, right? So we know, right, that mu is greater than epsilon, right? We know that delta is less than epsilon, is less than beta. So here's a chain of length 3, right? Since PM is 3 plus 1 free, right? Alpha is related to 1 of delta epsilon beta, right? But alpha, right, is not greater than delta. Right? Why is this? Because this is the leftmost bad thing, right? And therefore, right, this would be bad if alpha were bigger than delta, right? But this is the leftmost bad thing, right? So I think I've cheated on some details here, but this is the idea of the proof, right? That we just take everything in an odd component down here and switch it with everything an odd component down here. And of course, we have to show that when we exchange, right, when we make this adjustment W, then this becomes, right, a legal PM array with new shape, right, WRR plus 1 of lambda, right? So there's details to do, but I mean, I think enough is enough, right? So there's some sign reversing involution. And the last thing is, why does the claim hold? And I think I can do this in 5 minutes. Right, so the claim, I mean, was, it's somewhere, right here, this claim here, right? So what I've showed you is how to get from this formula to the formula involving just tableau without the signs, right, by this involution, right? Why does this hold? So basically, I'm interested in the coefficient of S lambda, and because the S's form an orthonormal basis with respect to the usual inner product, I'm just asking for the inner product of the chromatic symmetric function with S lambda. And now we're just going to apply the Jacobi-Trudi identity, which we discussed in the last lecture. This tells us how to write the S's in terms of the H's as a determinant, right, of a certain matrix full of H's. And so we're just going to expand the determinant the usual way. And I'm going to write it a little bit different, right? But if you check, right, the way I used W of lambda, this is true. This is the Jacobi and Trudi identity. So if you saw the terms we used, which was lambda sub W of I minus W of I plus I, right? It's sort of expanding by columns instead of by rows, but this is just the Jacobi-Trudi identity, right? And now, right, we just use that, the fact that M lambda, say H mu, is delta lambda mu. This thing here is nothing but the sum over all W in Sn, well, the sign of W times basically the coefficient of M in here. But if we have n variables, right, all we need is n variables to tell what's going on, because these are degree n functions. So this is nothing but the coefficient of one of the monomials I see in M lambda, x to the W of lambda sub I, right, in the chromatic symmetric function. So of course, I mean, I could be lying to you like crazy, but this is the right, right? This is the right use of notation, right? And now we can just ask how we get this thing. And I want to say this is the sum of all W and Sn sine W. And now what I want to say is this is the sum over all kappa, and I'm just going to define a set on the run. This kappa W lambda, I'll tell you what it is. This is T to the descent kappa. So here's where I was using that descent rather than ascent argument that Jim made for me. And this is just proper colorings, right? Satisfying kappa inverse of I, right? There's a lot of notation, but it's exactly, right, what we want, right? And this is the end. So I know there's some translation to be done, right? But I said that each array corresponds to a coloring, and the arrays, right, correspond exactly to these colorings. And so this is directly translates to the claim, right? So it turns out, right, that the reduction, the proof of the claim, right, is just using the inner product, right? these ideas, like I said, are all due to Gesharov. They aren't ours. And I think they're very beautiful, clever ideas. What we had to do was figure out the right sign reversing involution that, right, he just needed any sign reversing involution. We needed a sign reversing involution that preserved inversions. And so we had to look around a little and find the right one. I see it's exactly time to stop. I'm sorry I didn't finish early enough to leave, plenty of time for questions. But what we'll do next, we see now that this chromatic quasisymmetric function corresponds to a graded representation. So T is grading the representation, and we'll discuss what representation that is, which I think is in some sense the most interesting part of this work. All right, so thanks very much.
Yes, thank you, John. Any questions for John?
One last question, John.
Go ahead, Teddy.
You're going to show there is a corresponding representation now, but is it canonical?
So we have, essentially, we have the representation is in our hands, right? Because what we're saying is that the coefficient of S lambda in the teeth graded piece is the number of P tableau of shape lambda with exactly, if we're in the kth graded piece, right, exactly K inversions, right? And so we have a particular representation in our hand. We have no choice there. It's determined by the Hessenberg vector. The trick is to express it in some other terms. So what I didn't prove, but what we observed is that, in fact, if you look at the example, this graded chromatic symmetric function is in fact palindromic. Right, this S111 is the same as this S11. There's something in the middle. That's always true. And so if you just take dimensions, if I replace these symmetric functions by the dimensions of the corresponding irreducible representations, I have a palindromic polynomial. And what that indicates, right? So there's nothing sort of forced on me except the representation. But what that indicates is that this is the Poincare polynomial of a smooth manifold, right? It's palindromic, right? And it's certainly not true. So maybe there's a manifold with SN action, right? And Poincare duality doesn't have to be equivariant, but at least there's some Poincare duality going on here. So the idea is to find some manifold whose homology or cohomology groups admit the representations of Sn whose Frobenius characteristics are these symmetric functions, right? So this is what we made a conjecture which was proved by Patrick Brosnan and Tim Chow, right? So this is the sense in which I'm telling you something about the representation, right? Right here, I'm telling you what representation it is, right? But what we're going to say is this arises somehow naturally in geometry, right? And that, but that's not sort of forced on us. That's just something that's been discovered, right? So there's nothing sort of, my description is not canonical in any way. It's some association of these chromatic symmetric functions with certain manifolds. I hope that's useful and responsive.
Thank you, John.
Sure.
Well,
John? Oh,
go ahead.
I was going to ask, how did you figure out that these were the right manifolds to look at? Like,
this is a great question. So I have two answers, I think. The first is, as I said before, we knew a lot about the strings before we knew about the regular graphs. We discovered it through the strings. We started investigating the strings for a completely different reason. And Richard Stanley pointed out to us that certain representations we discovered were exactly, right, had Frobenius characteristics exactly the chromatic quasi-symmetric function of a string. And what we knew about that was that that was a representation on the cohomology of the toric variety associated to the Fana vial chambers, type A vial chambers. And then what was known is that thing lives in a family. That's an example of a regular semi-simple Hessenberg variety. So you can guess this way. And what we also knew from original work of Shaman and Damari and Shaman on Betty numbers of such things, you can compute the dimensions of these representations directly without knowing, actually. Right, if you know, say, the M decomposition or the P decomposition or any of them, you can compute these dimensions in a pretty direct way, and they match the Betty numbers. So then once we saw that, right, and in fact, I should say that's an exercise in EC2, I think one of the few exercises that's, you know, labeled 4 on it, right, is to relate statistics on these Hessenberg graphs to Betty numbers of these varieties. And so it was kind of sitting in front of us once we saw that things went well with the strings, right? It all kind of came naturally. But that's a good question, right? We started by noticing that you could use these strings to determine the joint distribution of exceedance and major index, which of the, you know, 4 natural pairs of Eulerian and Mahonian was the only one that was not understood. So that's how we started, and then we stumbled is too pejorative a word, but ran into this as we were finishing off that.
Thank you.
Sure.
I had one question. So your involution works for 3+1 free posets, but not, yeah, but they're not necessarily symmetric.
That's
But
correct.
they are quasi-symmetric, because there's some kind of positivity there in some kind of quasi-symmetric basis.
I believe that can be true, and now Michelle is here, and she can tell. So we know about, there's a theorem of Tim Chow's about expanding the T=1, right, symmetric function in the quasi-symmetric bases, and we have an analog of that also. And so that might well be correct, but I don't want to say.
Hey, any other questions for John or Michelle?
Yeah, can I ask, if you're looking for a scalar with any skew-sure function instead, does the proof just go through, or?
So I guess, let's have a look. Sorry, I'm trying to scroll with the wrong pad. So I guess, right, we want to go here. And you can certainly apply the Jacobi-Trudy identity. This is right, still right. I don't see why not, but I'd hate to be held to it.
Thanks.
So I guess, yeah, I don't see why not, but I'd have to think to be sure.
Yeah, the reason I ask is I was at OPAC, Anton Malik gave a talk where he said something about this case and attributed the proof to you guys, and I think he's right, and then it's the same, but I'm not sure either.
You could well be right. So you know, I learned a ton about my own work from watching Anton. So, but he was able to present a lot of these ideas in a completely different way than I understood them. But you know, it was correct, and so yeah, I saw that talk, and you know, how to say, you know, had I not heard my name mentioned, it would have taken me a little while to realize that it was our work. And he presented a completely different way, and I expect this is correct.
Okay, I guess that's it. Then we'll thank John again, and we'll see you on Thursday.
Thank you all very much.
Thank you.